Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Cold dilute KMnO4, Bayer's reagent, performs S-dihydroxyl of alkenes, adding two OH groups to the same phase of the double bond. Moving on to the next step. Identify the substrate. The structure shown is 1,2-dihydronaphthalene, a naphthalene-derived compound where one ring is aromatic benzene and the other ring is a cyclohexene with one double bond at the 3,4 position relative to the saturated ring. More precisely, the compound is a bicyclic system with a benzene ring fused to a cyclohexene ring. This is 1,2-dihydronaphthalene with the double bond between C3 and C4 of the non-aromatic ring. Moving on to the next step. S-dihydroxyl with cold dil. KMnO4 adds two OH groups in a S-ion fashion across the double bond C3 and C4, creating two new stereocenters at C3 and C4. And for the final step, analyze the stereochemistry of the product. The two carbons bearing OH groups, C3 and C4, become stereocenters. The S-ion addition produces the CIS diol. Because the molecule is fused to a benzene ring, the fused bicyclic framework makes C3 and C4 non-equivalent in terms of their substituents relative to the ring junction. Specifically, C3 and C4 each have different groups. One is adjacent to the ring fusion CH2 groups, and the connectivity differs. The key point is that the two stereocenters created are not related by an internal mirror plane in the product, so the compound cannot be meso. The S-ion addition occurs from either the top phase or the bottom phase of the double bond with equal probability. The reagent attacks both phases equally since the molecule has no facial selectivity bias from the aromatic ring side versus the open side. Actually, the benzene ring blocks one phase partially, but in this context both phases are considered. The S-ion addition from the top phase gives one stereoisomer, and S-ion addition from the bottom phase gives its mirror image, enantiomer. Since C3 and C4 in 1,2-dihydronaphthalene are not identical substituent environments, they are part of a ring, we need to check if the product has an internal plane of symmetry. The product is CIS 3,4-dihydroxy 1,2,3,4 tetrahydronaphthalene. At C3 and C4 both OH groups are on the same phase, S-ion. C3 is bonded to OH, C2, CH2, C4. C4 is bonded to OH, C3C4A, aromatic. Since C3 and C4 have different substituents, C3 connects to an aliphatic CH2, C4 connects to an aromatic carbon. There is no internal plane of symmetry, so the product is not meso. Because the two faces of the double bond in 1,2-dihydronaphthalene are enantiotopic, not homotopic, not diastereotopic, the molecule itself is achiral but the two faces lead to enantiomeric products. S-ion attack from one phase gives one enantiomer and S-ion attack from the other phase gives the mirror image enantiomer. Both are produced in equal amounts, racemic mixture, constituting an enantiomeric pair. Why other options fail? A meso compound would require an internal plane of symmetry in the S-ion addition product. Since C3 and C4 have different substituents, different ring environments, no internal mirror plane exists, not meso. C diastereomers. Diastereomers would result if two different S-ion addition products with different relative configurations formed, which is not the case here since only S-ion addition occurs giving one relative configuration, CIS diol, that exists as two enantiomers. D. Optically pure enantiomer would require facial selectivity, asymmetric induction, which does not occur with achiral KMnO4 on this substrate. Therefore, the correct answer is B. Therefore, the correct answer is option B.